Hello, this is Dr. Johnson, and I want to welcome you to today's lesson on the chi-square test of homogeneity. You will need your calculator to do the problem at the end of these slides. So let's begin. Last class, we talked about the chi-square test for goodness of fit. In today's lesson, we're going to talk primarily about the chi-square test of homogeneity, but I want to tell you right now that the mechanics for doing the chi-square test of homogeneity are identical to the mechanics for the chi-square test of independence. So there's a lot of overlap between them. The difference is primarily in how the data is gathered and how you write your null and alternative hypotheses. So let's begin with the chi-square test of homogeneity. This is a test to determine whether the distribution of a single categorical variable is the same for each of several populations or treatments. Suppose we take a simple random sample of male voters and a simple random sample of female voters. So we are stratifying by gender and taking two samples here. And then we ask the respondents whether they were Republican, Democrat, or Independent. You want to compare the distribution of political affiliation between these two populations. So let's look at the data. Do men's voting preferences differ from women's voting preferences? And the question here is, we are trying to look at whether the distribution of political affiliation, that is the Republican, Democrat, or Independent, so our variable is political affiliation, and we want to see if that distribution of political affiliation varies across gender. And here I have a sample of 400 men and a separate sample of 600 women. That is the observed data right there. Now, I will say this, in a lot of historical data, gender is treated as a binary variable. In the years ahead, we anticipate that more inclusive data may become available. So for today's lesson, just please pardon the binary gender identification. How do you write the null and alternative hypothesis? So here's how we do so with the test of homogeneity. I've written it generically, but I'll tell you how I would do it for this particular problem. There is no difference in the distribution of political affiliation across gender identities. That's the null. And the alternative is there is a difference in the distribution of political affiliation across gender identities. That's the null and alternative hypothesis for the chi-square test of homogeneity. Then we have to choose our significance level. If the problem doesn't give us a significance level, we're going to choose alpha equals 0.05 as by default. Now we check our conditions. Fortunately, the conditions for the chi-square test of homogeneity are the same as the chi-square test of independence. So let's get to them. For homogeneity, the data must come from using a stratified random sample or randomized experiment. And that's exactly what we have in this case. So that condition is met. Then we check the 10% condition. When sampling without replacement, we need to check that both samples satisfy the 10% condition. And that's satisfied in this problem here. Next, we check the large counts condition. All expected counts must be at least 5. And you must write out all expected counts. So how do you calculate expected counts? Here it is. The expected count for each cell in the table can be calculated using this formula. It's the row total times the column total divided by the table total. So what does that look like? Here on the top, I have the observed counts, and the table below I've created here is the expected counts. So how would you calculate the expected counts for the men who identify as Republicans? Well, I take the row total, that's this 400 over here, times the column total, that's this 450 here, divided by the table total, 1,000. So row total times column total divided by table total gives me 180. My expected count is 180. Now I have to do this for all 6 cells in our data. So these are all the expected counts, and as you can see, all of the expected counts are greater than 5. The lowest one is 40. It's right here. So we pass that condition. Now this is the mechanics of the test, and this is what your calculator will be doing for you. You don't have to do this. The calculator will generate your chi-square statistic once you put the data into the calculator. What is it doing? Well, it's the same process that we went through in the previous lesson. Here's your observed data. Here's your expected data. The calculator will calculate O minus E for each output. Then it'll square that quantity, then take the squared quantity and divide it by the expected value and add all of these up. It will come up, in this case, to a chi-squared statistic of 16.2. So our chi-squared statistic here is 16.2. The next thing we need to know is, well, what are the degrees of freedom? In the case of the chi-square test for homogeneity and independence, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So in this case, we had 2 rows and 3 columns. So I get 1 times 2 is 2. So in this problem, I have 2 degrees of freedom. Now, how do we come to our conclusion? Well, if the p-value is less than alpha, then you're going to reject the null hypothesis. And graphically, the p-value is the area to the right of our calculated chi-squared statistic under the density curve for the distribution with, in this case, 2 degrees of freedom. Equivalently, you can compare the calculated chi-squared with the critical chi-squared that you get from your table. We talked about this last time. If the calculated chi-squared exceeds the critical value, then you reject the null hypothesis. In this case, we have 2 degrees of freedom, so I'm going to go to row 2 right here. My significance level is 0.05, so row 2 and 0.05 tells me my critical chi-squared is 5.991, which is much less than my calculated chi-squared, so we reject the null hypothesis in this case. Your calculator will give you a p-value, and you can use your p-value. I think the more common way to solve this problem is to look at the p-value and compare it to your significance level. Keep in mind that the chi-squared tests only whether 2 variables are independent or homogeneous. It cannot address questions of causation, and it cannot check whether a category is greater than or less than. Strictly speaking, the chi-squared test only tests whether 2 variables are independent or not, whether they are homogeneous or not. If the chi-square test is statistically significant, then you will reject the null hypothesis, and you may be asked to do a contribution analysis. Only do a contribution analysis if asked, and if that is the case, if you are asked, then you're going to have to go to your the contribution table to see which outcome generated the greatest contribution towards your chi-square statistic. So let's do this problem right here. Here we have 60 volunteers, and they were randomly assigned. They randomly assigned 20 volunteers to get the red survey, 20 volunteers to get the blue survey, and 20 volunteers to get a control survey. So we got 3 different groups this time, not 2. We got 3 different groups, and they're the red group, the blue group, and the control group. The first 3 questions on each survey were the same, but the 4th and 5th questions were different. For example, the 4th question on the red survey was, when you think of the color red, what do you think about? In the blue survey, the question was they replaced red with blue. On the control survey, the questions were not about color. As a reward, the students let each volunteer choose a chocolate candy in a red wrapper or a chocolate candy in a blue wrapper. Here are the results. So we have 3 different groups, the red, blue, and control group, and we want to see if the distribution of color choice in candy is the same or different. So the question is this: do these data provide convincing evidence at alpha equals 0.05 level that the true distribution of colors are different for the 3 types of surveys? So that's because we have 3 different groups. It's going to be a test of homogeneity, and so we have to identify. Right? Here's the identify part. In the identify part, we want to state the significance level. So we want to test the following hypothesis at alpha equals 0.05. My null hypothesis is that there's no difference in the true distribution of color choice for people who get the red survey or blue survey or control survey. The alternative is that there is a difference in the true distribution of color choice for people who get the red survey, blue survey, or control survey. So that's the identify part. Now we got to check our conditions. And remember, we have to always, in this type of problem, we have to calculate all of the expected counts because we need to show that all of the expected counts are greater than or equal to 5. And so how did we do that? How did we get our expected counts? Here's how we did it. And when you create your table with expected counts, I want you to show me how you did at least one of the cells. So in this cell right here, the cell for red survey and red candy, I take the row total of 26 times the column total of 20 divided by the table total of 60, and I get 8.67. So you have to calculate all expected counts and show me the work for one of them. Oh, we need to talk about the other conditions. Yeah, random. The 3 treatments were randomly assigned. 10%. Because we are not sampling without replacement, we do not need to check the 10% condition. Remember, this is an experiment. And the large counts, well, we now see that from this table that all of the expected counts are at least 5. Now, let's go to your calculator. So I've got my calculator right here. I'm going to walk you through this process as well. And for the chi-square test for homogeneity, you're going to go to module 2, the stats module. Then you're going to hit test F3. Then you're going to hit chi, CHI for the chi-square test. That's F3. Now we are doing a two-way test. So the chi-square test of homogeneity is described in your calculator as a two-way test. So we hit two-way. Now you'll see that there's a couple options here. The observed data is in matrix A. The expected data is in matrix B. So we want to put the highlighter on the observed matrix A, and at the bottom hit mat with the arrow sign. So you want to hit F2 here. So hit mat with the arrow sign F2. And now you're going to be presented with a table for matrix A, and you want to enter the dimensions. So you want to hit F3 for dimensions for matrix A. And if I did this right, let's see if I did it right here. Now you're going to input the dimensions. So you need to specify the matrix dimensions for your table of data. M is for the rows and N is for the columns. So here in our problem, we have 2 rows and 3 columns. So M is 2 and N is 3. So now let's see what we do here. Now we hit 2 and 3, and then we hit enter, and you should be presented with a table that looks something like this. So now we want to enter the observed data in our table. So we enter our observed data. I'll give you a second to enter the data. Now you want to return to the test page by hitting exit twice. So I back up, I hit exit twice. And now I want to hit execute. I want to hit execute, and when I hit execute, it'll do my calculations and determine that the chi-squared test, the chi-squared statistic, is 6.65158. My p-value is 0.03594, and I have 2 degrees of freedom. So I want to write that down on my answer sheet. All that data goes right to the answer sheet. Now we need to show how we calculated that chi-squared statistic. The way we calculated it was actually with our computer, with our calculator, but we need to write out the formula with the numbers from the problem in it. So the first element in my chi-square statistic, I go to my first cell, and I take my observed minus my expected that quantity squared over the expected. And then I probably should do it for two different terms in my sequence, but in this case, I only did one. Then you write plus ... to represent the other terms in the sequence. Then you put the number that your calculator generated, 6.65. Now I want to write a little bit about how I got this number. So I did it with technology. And you could just basically write it. With degrees of freedom 2, technology revealed a p-value of 0.0359, because that's frankly what you did. But if you want to get fancy, you're welcome to do so. You can use the chi-squared CDF function. And your lower boundary is the chi-squared statistic of 6.65. Your upper boundary is some arbitrarily large number. We have 2 degrees of freedom, and that reveals a p-value of 0.0359. So our probability of getting a calculated chi-squared statistic greater than 6.65 is 0.0359. Now we have to interpret our results. So here's our interpretation. Because the p-value of 0.0359 is less than alpha, we reject the null hypothesis. That means we have convincing evidence in favor of the alternative, but we have to write that in context. So here's what we write. We have convincing evidence that there is a difference in the true distribution of color choice for people who get the red survey, the blue survey, or the control survey. So that's our lesson for today. Thank you very much for listening.